All right, in this video, we're going to look at some examples of work done by different forces acting on objects for a given scenario. Now, for each of these problems, we're going to start, just like we did with dynamics, with a free body diagram. This will help us identify the forces and the direction in which they act. Then we're going to find the work done by all the individual forces, sum them together to get the net work, and then try to connect that to the net force, and then figure out, is the object speeding up or slowing down? And this is where our work earlier with understanding the direction of the force relative to the displacement vectors should help. So let's take Pythagoras, and we're going to pull Pythagoras' head across the table with no friction. So no friction means if we have an applied force, I think we're pulling them with a string. So let's make this tension. Pythagoras' head has a weight. It's being supported by the table. And if it's pulled in that direction, it's going to accelerate in the direction of the pulling force. Therefore, it's going to undergo some displacement, delta x, in that same direction. So my delta x vector, I'm going to draw off of the free body diagram. So similar to what we did with acceleration vectors, to not confuse them with forces, we're going to draw them off. But important to draw them so we can recognize the difference between the direction of the forces and the direction of the displacement. Now, we have three forces. Let's figure out the work done by each one. So the work done by the normal force will be equal to the value of the normal force, the magnitude, times the displacement, times the cosine of the angle between the two. Now, in this case, normal force is perpendicular to delta x. So when I take the cosine of 90 degrees, I get 0. So when this force, in this case the normal force, is perpendicular to the displacement, it is doing no work. That means it's not causing that object to speed up or slow down at all based upon the direction in which it's acting. Now let's look at gravity. The work done by gravity will be the force of gravity times the displacement times the cosine of the angle in between that, and that's also 90 degrees, delta x and Fg. So again, gravity in this case is doing no work on Pythagoras' head. It's not causing it to slow down or speed up at all based upon the direction in which it's acting. Now let's look at the work done by tension. That'll be the magnitude of the tension times the magnitude of the displacement times the cosine of the angle in between it. Well, these are parallel to each other, Ft and delta x. So this is the cosine of 0, which is 1. So I get Ft times delta x will be the work done by the tensional force. So when I go here now to sum the work, the net work is just the work done by tension, which will be Ft times delta x, and that is the net work acting on my Pythagoras' head. Now, how does this relate to the net force? Well, if I were to sum the forces here, the net force is just the force of tension. And so this is the same as net work being equal to the net force times delta x, since Ft is the net force in this scenario. Now, will this speed up or slow down? Well, this is positive work since the force and displacement are in the same direction, so that will cause the object to speed up. Thus, it gains energy of motion, which is our kinetic energy, or sometimes we just label it as K. So there is Pythagoras' head dragged at a table, across a table, with no friction. Now, what if we were to pull with friction and a constant speed? So what changes here is that I still have normal and gravity, but now when I pull with tension to the right, I'm going to have a counter force, the force of friction, and these must be in equilibrium in order for there to be a constant speed. So just as in the problem before, the normal force and force of gravity do no work. So because they're at right angles to the displacement, so constant speed still moving in the same direction as before, no work because they're at 90-degree angle to the displacement. Tension is going to do the same amount of work because it's still, so the work done by tension is still Ft times delta x times the cosine of 0, which is 1. But now the work done by friction would need to account for. So that's going to be the force of friction times the displacement times the cosine of the angle between friction and delta x. Well, now friction is to the left, delta x is to the right. So what we've seen before now is these are anti-parallel to one another, or a theta of 180 degrees. And the cosine of 180 degrees is -1. So we get that this frictional force is doing negative work minus FFK times delta x. So when I go to find the net work, I take the work done by tension plus the work done by kinetic friction, and this will be Ft times delta x minus FFK times delta x. And if I factor out a delta x, it's just Ft minus FFK times delta x, and all this is the net force acting on the object. So if these are equal to each other, this is 0, therefore the net work done is 0 joules. So it maintains a constant speed, and if it's maintaining a constant speed, then there's no change or gain in kinetic energy. All right. So there are 2 examples. In the next video, I'll break it here. We'll look at 2 more examples of finding net work from individual forces.